Congratulations for making it here on Sunday morning. You don't have to stay awake because, of course, I get the wonderful opener, cardiac embryology. So feel free to fall asleep if you wish. Anyway, I'm going to look at my notes because I'm trying not to fall asleep too. So there you go. So I'm a nurse practitioner. I work in the paediatric congenital cardiac service across at Starship. I work with my colleagues that work with some of your people that are getting through into adult cardiology, and we're trying to communicate effectively with one another. But anyway, so moving on. So what I'm going to look at is a basic overview of cardiac embryology. If we get round to it, depending on the time, we'll look at some of the cardiac anomalies that might show up that are associated with various disruptions that happen during cardiac development. So just to start out with, I wanted to do a little quick overview of the heart so we're all on the same page when I'm talking about different things. To remind us that the heart is made up of 4 chambers, the 2 atria at the top, the left and the right atria, the 2 ventricles at the bottom, and they're divided by septums between them. The septum is an extension of the fibrous skeleton of the heart. The fibrous skeleton consists of 4 interconnecting valve rings and surrounding connective tissue, and this provides a rigid support for the attachment of valves and the insertion of cardiac muscle. It's also important to have your fibrous skeleton all intact because it also creates an electrical break between the top and the bottom part of the heart. You have valves, you have your atrioventricular valves, your tricuspid valve here on the right, your mitral valve on the left, and your semilunar valves, your pulmonary valve and your aortic valve, letting blood out of the heart. You have your great vessels coming in, your superior vena cava and your inferior vena cava, which are bringing back used blood or blue blood, as we talk about, from the body. The arteries, the pulmonary artery taking blood out to the lung, the aorta taking blood out to the body, and also your pulmonary veins that are returning blood that has been out to the lungs and is coming back oxygenated. So a quick little review of how blood flows. Blood comes back from the top half of the body via the superior vena cava, back from the lower half of the body by the inferior vena cava, into the right atrium, through the tricuspid valve, into the right ventricle, pulmonary valve, pulmonary artery out to the right and the left lungs, where the oxygen is picked up from the lungs, gets oxygenated. You now have pink blood coming back from, or oxygenated blood coming back from the left lung, coming back from the right lung, into the left atria, through the mitral valve, into the left ventricle, aorta, and out through the pulmonary artery, taking blood up to the head vessels in the top half of the body, and down around the gut, the bowel, and everything downstream. So that's how we roll. But let's think about how we start. So normally life begins when a sperm penetrates the egg and you have an exchange of genetic material. The fertilised egg is called a zygote, and the first 2 weeks after conception is called the germinal period, and this is where the zygote divides and divides and divides and also attaches into the uterine wall. During this rapid division, there's also organisation of the cell, so that by the time you get to this guy out here, the blastocyst, you've got a hollow sphere, cells on the outside, and it's in this blastocyst that you start getting the differentiation of, or distinctive layers of cells and different things that they're going to do. You have the ectoderm, which is the external covering, the skin, the nerve endings and all that sort of stuff. The endoderm is the digestive system, the respiratory system, and differentiation continues to occur at about 16 days. We see another layer, and this is the mesoderm. This mesoderm becomes the basis for muscles, connective tissue, and for us, because we're going to talk about the heart, the circulatory and excretory organs. So the primitive heart, its cardiovascular system is the first system to function in the embryo. it's during the first 18 to 20 days of life, so the first 3 weeks, the human embryo doesn't have a cardiovascular system, but by 21 to 23 days of development, you have contractions of the heart with forward blood flow present. By 24 to 26 days, you have a beating heart with a regular heart rate. And by 8 weeks, you have a heart and great vessels have completed their development, and they look very much like what a term baby will be, or an adult. It's just a whole pile smaller. So there's a lot of growing to do. So it's an amazing process, and it happens pretty much within 8 weeks, and you end up with a 4-chambered vessel. So this picture here is showing you a fetus about 4 weeks of gestation, showing the developing neural tube, and the heart, at this stage, while not developed or fully developed, is actually beating. And then this is a picture showing you a baby or a fetus at 8 weeks that has a fully formed heart at that stage. So we do quite a lot of growing in that first part of our life. The heart is the first organ to function within the embryo. The heart initially forms from 2 tubes that are located bilaterally on either side of the embryo in the cranial or head part of the you can see where I've taken those pictures from. The head part, it makes its first appearance while the embryo is still flat at the extreme head end of the embryo, when clusters of mesoderm cells specialise to form the early blood cells that go on to become the heart. And this is called the cardiogenic area or cardiogenic plate. So this is shows you these primitive tubes developing in the embryo at approximately 18 days after conception, and it shows these clusters of these mesodermal cells near the head end of the embryo, and this is looking at it in the sagittal view. So I put these pictures in, and hopefully you won't see where I got them from, but this is this picture shows the cardiogenic area that's in the square box, visible in the developing embryo. So you've got these serial pictures from 20, 21, 22 days, and it shows you how quickly we are forming, and our heart is growing dramatically. And it grows so fast that actually, even when your embryo hasn't sort of curled on itself, which comes next, you've got this cardiac bulge that's already showing you how quickly the fetal heart is developing. So the next phase, which is around 4 to 8 weeks, is embryonic folding. This is where the embryo changes from a flat disc into a 3D cylinder through a process called embryonic folding. And this is when both the cranial or head end and the lateral end fold towards each other. There's rapid development and flexion of the head part of the embryo. This is the head fold, which causes the cardiogenic area to move from right at the top, it tucks back in and comes to lie below the head and the mouth and in front of the foregut. And the lateral fold, which is the tail end of the embryo, is folding forward. It's the forerunner to the gastrointestinal tract, and it's simultaneously folding at the same time, and it forms the tail and brings the anus into the eventual adult position. So as I mentioned, the start of the primitive heart is derived from the mesoderm, that following cell signalling, and when I did quite a bit of reading about cell signalling and fell asleep. So as you can see, that I've put a few of the really important cell signalling hormones there, just to cardiac specific genes are expressed on these 2 guys here, and that's my summary of cell signalling. But basically, you start out these 2 longitudinal strands that are hollowed, and they are forming these endocardial tubes. These tubes migrate towards one another and fuse together to form a single straight tube, which is anchored at one end by the arterial end and anchored at the other by the venous channels. With fusion of these two tubes heading towards each other, what you see are areas of narrowing and areas of dilatation appear in the heart tube. And there are 5 distinctive regions, and listed from the head to the tail. You have the truncal area, or the truncus arteriosus. That comes on to end up being your pulmonary artery and your aorta. You have your bulbous cordus. The bulbous cordus will become the right ventricle, so that's the bulbous cordus. And then you have the ventricular part, that becomes the right and the left ventricle. And you have your primitive atrium, which forms the front part of the the left and right atrium. And down here you have the venous sinus venosa. This is the most tail segment of the cardiac tube, and it becomes the major veins carrying blood into the heart, as well as parts of the right atrium. So remember that by day 22, this little thing here is contracting. You've got blood flow initially flowing from the sinus venosus end and out, so going from tail to head, going out through the sinus venosa. So the next thing is cardiac looping. That starts around day 23, and basically the tubular heart undergoes a process of looping to eventually end up forming the shape of the adult, that of the adult heart, and as I mentioned, regulated by a cascade of genes that are essential for left to right programming. That means that the right ventricle ends up on the right and the left ventricle ends up on the left. This looping occurs because the heart is in a confined space. Remember I said the heart's growing faster than anything else of the embryo, and it's fixed at both ends. So this guy is held and this guy is held, and the tube itself is growing, and by growing and being fixed, the loop folds forward and to the right, and that's called D-looping, or dextral or D-looping. And that fold, so initially the heart looks a little bit like the letter C. So this bulbous area, it's mostly in the bulbous cordus and ventricle area that folds forward, so toward anterior and to the right. Initially the heart tube forms the letter C. And then you start to get the S shape where the atria, these are the atria down here, start to come up and forward and to the side, and they form this letter S. So they go backwards and then up. I always think about Princess Leia with her things on the side of her head, and you end up with the various chambers of the heart essentially getting in the right spot. So the cardiac tube grows at greater longitudinal length rate than the rest of the embryo, causing it to fold. As it does this, the cardiac tube is pushed forward and to the right, causing known as D-looping. Picture, you can see that this grows really fast, telling you the difference in a couple of days, 10 hours, beg your pardon. This picture here is showing you a D-looped heart with the cardiac tube looping to the right and forward. If you get that wrong, and if the loop goes the opposite way, then you've got what's known as an L-looped heart. So this little picture down here is a chick embryo. Here's your normal D-loop, and here's a loop that went the wrong way, went to the left. In that situation, what you could get is ventricular inversion occurring when the morphological left ventricle is now lying on the right-hand side of the body. So all that's happening on what you can see on the outside, but there's lots of stuff happening inside the cardiac tube. So we'll slice through the heart and we'll have a look and see what's happening inside. So the internal heart undergoes lots of changes in order to form the atria and the ventricles of the adult heart, and it involves separating the left and right, but also separating the atria from the ventricles. And it does that by developing an intraatrial septum, an intraventricular septum, endocardial cushions or AV cushions, and the spiroaortopulmonary septum. So we're going to go through this. Stick with me. Not much longer now. So, separation of the atria and the ventricles begins with the cells from the back and front walls of the heart start growing, form these two protrusions. So here and here, these are the endocardial cushions or swellings of the cardiac tissue. And they start to appear at around 4 weeks of gestational age. They grow inwards and towards one another with the aim of separating the atria from the ventricles. They grow towards each other and fuse to form the left and right atrioventricular canals. These bulges have the appearance of valves, but they might play a fairly important role in the development of valves, but the eventual formation of the tricuspid and the mitral valve, the endocardial cushions are not the precursor to that, and I didn't spend a lot of time reading that, so don't ask me any questions about how the valves are formed. Okay, so now we know where we stand. So at the same time as the atria is dividing, so these endocardial cushions are coming towards each other, and we get this, the common atria, you get this thing called the septum primum that starts to grow down from the roof of the atria to start to subdivide the atrial chambers. In the ventricle, so simultaneously in the ventricle, you get a interventricular septum that starts to grow up from the floor of the primitive ventricle to subdivide the ventricular chambers into the left and right ventricle. And it's initiated by this muscular ridge that grows out from the apex of the heart, and it's very thick muscular tissue. Back in the atria, that septum primum that was growing down is now becomes perforated. So here's your septum primum. This becomes perforated, and it forms a gap or a hole, and this is allowing blood to shunt from the right side of the heart to the left side of the heart. In the fetus, the right-sided pressures are higher than left-sided pressures because where this blood is being delivered to is theoretically the lungs, except the lungs are like, there's no air in them and it's really difficult for blood to go that way. So the pressure is high in this right side compared to the left. So in the ventricles, the ventricular walls are thickening, and the interventricular septum is continuing to grow upwards towards the endocardial cushions, and there's a small, there's a forum or gap that exists between the left and the right ventricles, and this later closes with the formation of the aorta and the pulmonary arteries. So that gap closes, one, because the septum is heading towards each other, but also because of the aorta and the pulmonary trunks are doing their thing at the same time, which we'll get to. So at this stage, the development, there's a communication between the left and right atria, and also between the left and right ventricle. But up here, can you see a little second septum? The septum secundum starts to grow down from the roof of the atria. It's just that little nubbins just there is starting to grow down. It starts heading towards, and it's on the right of the original septum primum that broke apart. Back in the ventricles, the interventricular septum fuses with the endocardial cushions, forming the two separate left and right ventricle, and that happens with the simultaneous formation of the aorta and pulmonary arteries. And with this, the ventricles are now separated, and the valves begin to develop, and they start around 5 to 8 weeks of gestation. In the atria, that septum secundum has now grown down from the roof of the aorta, and it grows down to cover the opening of the septum primum. So it keeps growing, goes past where that gap is. And the overlapping of these two tissues or septums create the foramen ovale, which remains open in fetal life because of the high pressure on the right compared to the high pressure on the left. But what happens at birth is that the baby takes a breath, the lungs inflate, more blood is able to get to the lungs because the blood vessels out in the lungs are more wide open, so blood can go there more easily. So more blood is going out to the lungs, more blood therefore is coming back to the left side of the heart, and what was a low pressure is now higher than the pressure on the right. So that little flap valve closes because of the pressure on the left side, and that closes the foramen ovale. So you've now separated your atria. You have a left and your right atria. Now backing up a bit, we're going to talk about the formation of the aorta and pulmonary artery. And remember we had the truncus arteriosus, which was the large vessel coming out the top of the heart, and it's this truncus that divides to form the aorta and pulmonary artery. So we go back to this picture. I know you love it. This is, remember I said that this guy was anchored, and this guy was anchored, and this is the cardiac tube is moving forward and to the right. So what happens to this little trunk out here, or rather to the aorta, is it gets pulled. And with the looping of the heart, the arterial trunk is dragged over to the right, following the loop that's heading that way. It's over to the right, and it's also twisted. So it ends up being in a spiral shape, not because the inside of the aorta and pulmonary is spiraling, but it's been pulled in that direction, and it's moving me on to the next slide, which is probably a good thing. So inside this twisting truncus, you have the formation of the aortopulmonary septum, by 28 days, the truncus has managed to divide itself into the pulmonary channel and the aortic channel by the formation of the aortopulmonary septum. And it does this, and so if you chop those vessels in half and had a look at them on the cross section, you would see that the aortopulmonary septum forms as a result of growth of ridges of truncal swellings that protrude from both the aorta and the pulmonary sides of the vessel. They expand and twist towards each other, eventually fuse, creating the pulmonary artery and the aorta. And these swellings also develop the pulmonary and aortic cusps. So finally, just looking at this again, with the looping of the heart tube, the arterial trunk is dragged towards the right and twisted. This looping brings the trunk, remember I said that the ventricular septum is coming up, but at the same time this vessel is looping, and the looping brings that trunk really close between the opening between the atria and the ventricle, and it's known as the AV canal. As a result, the ascending aorta comes to lie to the right of the pulmonary artery. So normal division of the great vessels results in the location of the aorta lying behind and to the right of the pulmonary artery, and the pulmonary artery is to the left and anterior of the aorta. And when these great vessels are in the normal position, they're labelled derelated great vessels. So you've done it, you've got through. You now know how the heart forms. Know nothing about cell signalling, but I'll leave that up to you to read in your spare time. So there's a variety of congenital abnormalities associated with inadequate completion of the various stages of cardiac development. I've done, probably got more than we've got time for, since I'm due to finish in about 2 minutes, so we'll just whip through. So there's those with, that are associated with inadequate formation of the atrial septum. It's never as simple as this, you know, like you belong in different categories, but you know, an atrial septal defect or an AV canal. So an atrial septal defect is where the septum between the atria hasn't formed properly, and you therefore have a gap between the two atria, allowing, as that child gets older, remember I said pressure after birth on the right hand and the left hand side is higher than the left, so blood shunts from the right to the left. Then there's those associated with inadequate formation of the ventricular septum, like VSDs or Tetralogy of Fallot. So ventricular septal defects is where, for whatever reason, the septum between the ventricles haven't formed. It can be about the septum itself. It can also be the aorta and the pulmonary not lining themselves up appropriately. But this, again, pressure is higher on the right than it is on the left, so blood will shunt from the left I've said that the wrong way around. Blood is higher on the left than it is on the right, so blood will shunt from the left across to the right. And I threw some pictures in there again. Don't ask me to explain those too much, but here's showing you a break in the septum and various places that they can be at. There's also anomalies associated with inadequate formation of the endocardial cushions, like AV canal defects, ASDs and VSDs can be included there, and mitral and tricuspid valve defects. So endocardial cushion defect just is one example of atrioventricular septal defect. So the septum hasn't developed between the atria and the ventricles and the endocardial cushions. So that whole area is a bit sort of scooped out in there because it didn't really develop. So there's free communication between the chambers, and blood, of course, is going to shunt from the left to the right-hand side because pressure is greater on the left compared to the right. So you have a child or an infant that will have signs of they'll be breathless and puffy and all that sort of stuff. Panty is what I mean. And then anomalies associated with inadequate truncal formation, Tetralogy of Fallot, transposition of the great arteries, truncus arteriosus, as well as things like pulmonary atresia, aortic stenosis, and AP window. So just a quick little look at tetralogy. Tetralogy is where you have a narrowing going out to the pulmonary artery. It can be below at the valve or above the valve, and you have a VSD, as well as an aorta that's kind of shifted to the right, so it's a bit overriding, and over time you get ventricular hypertrophy. Transposition of the great arteries, where in that forming the aorta hasn't managed to get to the left and the pulmonary hasn't managed to get to the right, and you have side-by-side vessels. So your aorta is coming off your right ventricle and your pulmonary is coming off your left ventricle. And we won't do any more. I think I'm done because I've run out of time. So thank you very much.